Okay, so in this video, I am continuing our discussion on the topic of gas mixture, or basically chapter 13 of our textbook. And we are going to study the properties of ideal gas. So, uh, first of all, the title is PVT, behavior of gas mixtures. Okay, so before I start this discussion, let me review the concept of ideal gas versus real gas. So we know that gases behave either as an ideal gas or as a real gas. As a real gas. This is what we know from before. Now, the question between these two is, in ideal gases, the equation of state is PV equal to RT. But so that was in ideal gas, but in real gases, PV is not really equal to RT. There is another coefficient on the right hand side. So generally, we can say that if this is the equation of state for a gas, pressure multiplied by a specific volume equal to Z, which is called the compressibility factor, or gas constant, and T the temperature. So this can be a general equation for gases. And if the value of Z is equal to 1, then that gas will behave as an ideal gas. But if the value of Z is not equal to 1, is either less or greater than 1, then the gas is behaving as a real gas. This is just a name that they have put for that. So that is why usually when it comes to ideal gas problems, we just do PV equal to RT. We don't even put down this Z. In fact, there is a Z there, but because for ideal gas that Z is equal to 1, we never write it down, or usually we don't write it down. Now, here's the question. The question is, if we have a mixture of two or more ideal gases, so let's say we have different ideal gases, and obviously they are following the equation of PV equal to RT because they are ideal gas. Now the question is, if that mixture is also behaving as an ideal gas. So once again, imagine that we have a tank. In this tank, we have two or three or even more components. For the sake of simplicity, I just do two components. Let's say I have the blue component, let's say the gas shown in blue, and this is behaving as an ideal gas. And also I have the red component, there is another gas, and that is also behaving as an ideal gas. So each of those two components are behaving as an ideal gas separately. Now the question is, what about the mixture? Does the mixture behave as an ideal gas? So question is, in red, does the mixture of two or more ideal gases behave as an ideal gas? So the short answer is yes. Whenever we have two or more ideal gases or components that are behaving ideally, and if there is no reaction between the gases, then the mixture is also behaving as an ideal gas. So a good example is air. Air is the mixture of nitrogen and oxygen, right? Nitrogen is behaving as an ideal gas in room condition or room temperature and pressure. Likewise, oxygen is behaving as an ideal gas. So the mixture of those two, which is air, is behaving as an ideal gas. So the answer is, or just a bullet item which relates to this question says, when two or more ideal gases are mixed, the behavior of non reacting mixture of ideal gases also behaves ideally. So example, air. So air itself is behaving ideally at room condition, let's say, because definitely there may be some conditions that air is not behaving ideally. But let's say air is behaving ideally in room condition. Likewise, I mean, before that, oxygen and nitrogen, which are the two main components within the air, they are also behaving ideally. So because of the fact that oxygen and nitrogen were behaving ideally, the mixture of them, which we tend to call it air, is also behaving ideally. Okay? So at the end of the day, if we have components which are already behaving ideally, their mixture is behaving ideally as long as there is no reaction between the two components or two or three or more components. If there is a reaction between them, let's say if there is a combustion, then that's another story. But in our course, we are not really discussing about combustion or any other sort of reaction. Okay, so if we have like components which are behaving ideally, their mixture is also behaving ideally. Now, what about the PVT behavior of those gases? Now, that PVT behavior, pressure, volume, or specific volume and temperature behavior, is evaluated based on two different approaches. So, the PVT behavior of gas mixtures. In one approach, we can just treat them by adding their pressures, by adding up the pressure of each component to obtain the pressure of the mixture. Okay, and that will be called the Dalton's law of additive pressure. So what we are doing in this approach, we are just adding up the pressure of each component to each other to obtain the pressure of the mixture. We can also look at their volume, okay, and that will form the Amagat's law of additive volume. Okay, so what we are doing in this approach is, in order to obtain the volume of the mixture, we are adding up the volume of each component to obtain the volume of the mixture. So in Dalton's law, the pressure of a gas mixture is basically equal to the sum of the pressure of each component. The pressure of the gas mixture is equal to the sum of the pressure of each component. Well, I need to clarify that. Well, that pressure of each component, in case that was alone within the mixture at the same temperature and at the same volume. The pressure of each component is evaluated at a condition at which that component was the only component in the system at the temperature and volume of the mixture. Now, this is a little bit complicated, or at least it looks complicated. So what I'm trying to say by this sentence is, let's say we have three different components. Let's say we have component A, component B, component C, all of them in a tank. If we want to do the Dalton's law, then let's say we are starting with component A, we are ignoring B and C. So we are pretending that only component A is within the tank, all right? And we are evaluating the pressure of component A at temperature and at volume of the mixture. So the volume of the mixture, let's say, is the volume of this tank. And the temperature of A is assessed or evaluated at the temperature of the mixture. Now that gives us a certain pressure. We do the same thing with B, the same thing with C. Now we have maybe three different pressures, maybe two of them are equal to each other, but let's say we have unique pressures for these components. Now in Dalton's law, what we are doing, we are adding up those pressures together to come up with the pressure of the mixture. So this is what I was trying to mention. So definitely I will do some problems so you will see how this thing works. So basically, if I want to do a very simple schematic, I would say, let's say, according to Dalton's law, let's say we have gas A, okay, and we are combining gas A with gas B, okay, but both of these two gases are at same volume at same temperatures, okay. Gas A has pressure of PA and gas B has pressure of PB. Now the mixture of these two, okay, gives us another gas which is called the mixture of A and B, let's say, or you can call any other name for that. The temperature is still the same because this T and this T is the same as this T, and volumes are also the same. So the volume of this tank and this tank and this tank, all of them are the same volume. But the pressure of here, the pressure of the mixture is the pressure of A plus the pressure of B. Okay, so these two gases as well as the mixture are evaluated at the same temperature and also the same volume. So volume doesn't really change, but the pressure is sum of these two pressures. So that is the Dalton's law. Now, after Dalton's law, we can have the Amagat's law, which the concept-wise is pretty much the same, but instead of dealing with pressure, we are dealing with volume. Okay, so Amagat's law So according to this law, the volume of a gas mixture is equal to the sum of the volumes each gas would occupy if it existed alone at the mixture temperature and pressure. Okay, now here, if I want to do the schematic, I would say, let's say we have gas A at pressure of P and temperature of T, that's a specific condition, and the volume of this gas, let's call it it's VA. Okay, we are mixing this gas with gas B, which is at pressure of P and temperature of T, but volume of VB, another volume. So according to Amagat's law, then the mixture of these two is another gas. So let's say mixture of A and B, whatever name you want to put for that, and the pressure and temperature are the same. So basically these pressures and temperatures are the pressure and temperature of the mixture. Okay, so these are following these, but the volume here is going to be volume A plus volume B. So we are adding the volumes in the mixture. So that is based on the Amagat's law. Now, the Dalton's law and the Amagat's law gives us exact result for ideal gas. So there is no approximation when it comes to ideal gas. Okay, the Dalton's law and Amagat's law result in an exact answer for ideal gases. So let's say if our components are already behaving ideally, and if we apply any of these two laws on the mixture, then the answer, whatever pressure or volume we are looking for, is the exact answer. There is no approximation. However, things are different when it comes to real gases. So basically, the Dalton's law and the Amagat's law result in an approximated answer in real gases. So the second bullet item is assuming that our components at the beginning are behaving as real gases. So let's say the components are behaving as real gases. We mix them to each other. We apply either the Dalton's law or the Amagat's law to obtain the properties of the mixture. But those answers or those properties are approximated answers. They are not exact answers as we would have if the gases were behaving ideally as at the beginning. Now, the Dalton's law can be written as Pm, the pressure of the mixture, is equal to the pressure of each sum of the pressure of each component at the temperature of the mixture and at volume of the mixture. It's very important that the pressure of each component be evaluated at the temperature of the mixture and at the volume of the mixture. And this I starts from to 1 to k number of components that we have. Now that k can be 2, can be 3, all the way go up depending on the number of components that we have. Likewise, the Amagat's law is saying that the volume of the mixture is equal to the sum of the volume of each component at pressure of the mixture and at the temperature of the mixture when I starts from to 1 to the kth component. Okay, now we have like two definitions or two properties. One property is called the pressure fraction, and that is shown by Pi over Pm. Okay, Pi is the pressure of one particular component and Pm is the pressure of the mixture. Likewise, we can have volume fraction. And volume fraction is the volume of component I to the volume of the mixture. Okay, so let me go back into here and make it clear that this is not the specific volume. This is in fact volume. Meter cube, for instance. This is not the specific volume. Okay, so I can provide one simple schematic that shows the Amagat's law. For example, let's say if I have this mixture, which is mixture of oxygen and nitrogen at 100 kPa, and 400 Kelvin and 1 meter cube. According to Amagat's law, this can be the mixture of these two systems. So I have two separate tanks at the beginning, let's say oxygen at same pressure, 100 kPa, and same temperature, but smaller volume, let's say 0.3 meter cube, and nitrogen, again at the same pressure, at the pressure of the mixture, at the temperature of the mixture, but at a smaller volume. So what happens here, these are the two components that we have. We have nitrogen and oxygen. So both of these two components are at the same pressure, which is the pressure of the mixture. So this is the mixture here, all right? The pressure of the mixture is 100 kPa. Each component is also at 100 kPa. Also, the temperature of the components is the same as the temperature of the mixture, 400 Kelvin. Now, the Amagat's law says the volume of the mixture, which is 1 meter cube, is sum of these two volumes, 0.3 meter cube and 0.7 meter cube. So this schematic is according to the Amagat's law. Okay, now what about the ideal gas mixture? Like, what are the correlations for the ideal gas mixture? So ideal gas mixture. What I'm going to do, I am starting with Pi over Pm. So Pm is the pressure of the mixture and Pi is the pressure of component I. Okay, so Pi over Pm. So Pm has temperature of Tm. So this is the temperature of the mixture and volume of the mixture. So basically, the pressure of the mixture is evaluated at the temperature of the mixture and at the volume of the mixture. Also, I'm going to assume that the component I, the pressure of the component I is evaluated at the same temperature and at the same volume, which is the temperature of the mixture, the volume of the mixture. Now, because we are dealing with ideal gas right now, or at least this part of the discussion is about the ideal gas, I can write the pressure based on the ideal gas law. So the ideal gas law says pressure is equal to the number of moles in the mixture multiplied by the universal gas constant multiplied by the temperature of the mixture divided by the volume of the mixture. So PV equal to nRUT, N being the number of moles. Likewise, I can apply the ideal gas law to rewrite Pi, or basically I can solve Pi based on the ideal gas law, and that will be the number of moles in component I multiplied by the universal gas constant Ru multiplied by the temperature of the mixture divided by the volume of the mixture. The reason is component I has the temperature of the mixture and the volume of the mixture. Okay? Now, I can simplify this Ru with this Ru, this Tm with this Tm, and this Vm with this Vm, and I will end up with Ni over Nm, the number of moles in component I over the number of moles in the mixture. But guess what? This ratio is called the mole fraction that we had before, which we showed that with Y. So this is our mole fraction. So basically, if we have a mixture of ideal gases, the pressure ratio, or Pi over Pm, is equal to the mole fraction. Or I should say, instead of pressure ratio, I should say, where was it here? The pressure fraction is the same as the mole fraction. Okay, so that means I can obtain the partial pressure so I can say that Yi, which is mole fraction of component I, multiplied by Pm, the pressure of the mixture, is equal to the partial pressure. Okay, so the partial pressure is yi multiplied by pm. So this partial pressure is pi that we have here in the previous slide. If you see, pi is equal to pm multiplied by yi. Okay, I can also have partial volume, and that will be yi multiplied by the volume of the mixture. So that will be partial volume. So the point is, if we have an ideal gas, for the ideal gas mixture, the mole fraction, the pressure fraction, and the volume fraction of the component, all of them are identical. For an ideal gas mixture, the mole fraction, the pressure fraction, and the volume fraction of a component are identical. All of them are the same value. Value-wise, they are all the same. So we show the mole fraction with yi. We show this pressure fraction with pi, and this volume fraction with vi. So all of them are the same for a component in an ideal gas mixture. So that was for the case that the components were behaving as an ideal gas, and also the mixture was behaving as an ideal gas. But the question is, what if we are dealing with real gas? How about the real gas mixtures? So that will be the title. Okay, the thing is, the Dalton's law and the Amagat's law can still be used with a reasonable accuracy. Okay, so let me just write it down. The Dalton's law and the Amagat's law can be used with reasonable accuracy. So that means applying the Dalton's law and the Amagat's law does not give 100% exact value, but still that is reasonable, that is close enough to the actual property. However, the deviation of component pressure and volume from ideal gas behavior should be evaluated. Okay, so we are starting with real gas components, right? Those real gas components, they have their own z value in PV equal to ZRT. Now, we want to come up with a new z that averages all those z for components. So let's say if for ideal gas we have equation PV equal to z n RUT. So this is the general equation, either ideal gas or real gas. When the z is equal to 1, that is for ideal gas. When z is not equal to 1, that will be for a real gas. So what we want to do, we want to evaluate or obtain the z value for each of those components. And based on that, we are going to obtain the z of the mixture, z of m, by just adding up yi multiplied by zi, okay? And I starts from 1 to k. So here zm is the z for the mixture, zi is the z for each component, or let's say component I, and this is the mole fraction. Okay, mole fraction multiplied by the compressibility factor, and if we do that for all components, that will give us the zm, or z for the mixture. Now, if we are dealing, or if you're working on Dalton's law, then Zi will be based on the temperature Tm and the volume Vm. So Zi from Tm and Vm in Dalton's law. Okay, so if you are working with Dalton's law, then Zi, or the Z value for each component, is evaluated at the temperature of the mixture and volume of the mixture. Likewise, if you are working based on the Amagat's law, the Zi is assessed at the temperature of the mixture and pressure of the mixture. Zi from Tm and Pm in Amagat's law. Again, you will see that in a problem, in a sample problem. Now the question is, do we get same result for this concept? Do we get the same result if we go with Dalton's law and with the Amagat's law? Are they ending up with the same answer? The thing is, no, we do not get the same result in these two approaches. The Amagat's law basically gives a more accurate result simply because in Amagat's law, we are considering the pressure of the mixture, okay, and that pressure represents the influence of the intermolecular forces between the molecules of different gases. Okay, so let me write these as a question. So question, do we get same result by considering Amagat's law or the Dalton's law in Zn equal to sigma yi zi? Okay, so do we get the same answer for? So to answer this question, we need to realize that in Amagat's law, the properties are evaluated at the mixture pressure. So the answer will be no. Amagat's law gives a more accurate result since it involves the use of the mixture pressure, which accounts for the influence of intermolecular force between the molecules of different gases. So what we are doing in Amagat's law, we are evaluating the properties at pressure of the mixture Pm. Because the properties are evaluated at this pressure at Pm, then the influence of the intermolecular forces between the molecules are also considered. So because of that, the Amagat's law is more accurate when it comes to use this equation. Finally, there is another method or approach in evaluating the properties of a real gas mixture, and that is by treating the gas mixture as a pseudo pure substance. So that approach is basically the K's rule, and what we are doing in this rule is the PVT behavior of a gas mixture is treated based on a pseudo pure substance. Okay, so basically what we are doing, we are defining a pseudo pure pressure, or let's say pseudo pure critical pressure. So this is the critical pressure of the mixture, but we are considering the mixture as a pseudo pure substance. Basically, we are considering the mixture as a new substance which has its own property. Likewise, we are considering the pseudo pure temperature, or I should say pseudo pure critical temperature. So that is T critical of the mixture, and that is prime basically. So basically, this pressure, this P prime critical of the mixture, is obtained by y sigma yi P critical of each component, and I starting from 1 to k. Okay, so what we are doing, we are obtaining the critical pressure of the mixture by multiplying the mole fraction to the critical pressure of each component and summing up all the components. We are doing the same thing for the temperature. So the critical temperature of the mixture is obtained by multiplying the mole fraction of each component to the critical temperature of that particular component. So we are doing one example on this concept.